Eliška. Okay, yeah. So Professor Eliška Greplová, and I hope I pronounced it correctly. So she's assistant professor at the Department of Quantum Nanoscience at Delft University of Technology. And with her group, she works on quantum technologies, AI, and condensed matter physics. And she's also a member of the World Economic Forum Network on Global Future Council on Quantum Computing. And she's member of the organizing committee of Virtual Science Forum, a platform for fully digital scientific events. So today in our talk, she is presenting the automated control, I can see now, and characterization of quantum devices. So Eliška, the stage is all yours. Thank you very much for being here.
Thank you so much for the nice introduction, Fulvio, and many thanks to the organizers for having me. I'm enjoying this conference tremendously, and it's so well organized. I'm really looking forward to chat with all of you. So, as Fulvio just said, I want to tell you a bit about our work on automated control and characterization of quantum devices. And specifically in this talk, I am going to mainly discuss quantum dots as a platform. So let me maybe start by repeating the main question of this session. You know that this conference is organized around these three very targeted questions. So for this session, we have, how can we achieve fully automatic calibration and operation of multi-qubit circuits? So this is something that I'm going to try to answer today. It's a very pressing questions nowadays when our qubit circuits are scaling up, and we all know how much complexity comes with controlling and calibrating them. So given the topic of this conference, it will be no surprise that my talk is at the boundary of two things, specifically quantum devices and machine learning. Namely, how can we use some of these modern algorithmic techniques to control and tune and characterize some of these devices. So back to this question 2 that I cited at the beginning, I want to split this talk into two and give kind of two answers or address two aspects of answering to this question that I believe are both valid and important. So first challenge that we have is something that I like to think about as a front-end challenge, that you have some kind of device, you are reading out data directly, and you would like to turn this data into some control parameters that you adjust, such that you can find something like a minimum in your optimization landscape. This is typically not super simple because you have to adjust multiple parameters at once. And it's also quite complex because our data can be like device dependent and many other things dependent. So typically this requires quite a lot of intuition and experience. So stuff like a simple for loop with 8 criteria to check is not going to do. So that's the first thing, just like thinking how to translate this data into control and tuning directly on the device. Second thing that is more theoretical, but I think that is a valid and important research direction as well, is the learning physics of your quantum device. What we've seen also in other talks in this conference, and what I'm going to address a little bit later on, is that when we are trying to do this kind of front-end control, accumulating measurements and turning them into optimization in this multi-parameter landscapes, we have a data problem. As in the number of parameters we have to adjust and amount of data we need to tune these things in the first case does not scale so well with number of qubits. So this question of characterizing the physics of your quantum device, for example, running Hamiltonians or reconstructing wave function, and then creating from that knowledge some very compressed characterization of your device, or getting new ideas for the more stable qubits and things like that, I think is very important as well. So, but let me start with this first challenge, which is automated control of the quantum devices. So in this conference, you've heard plenty amazing stuff about quantum dots already, but just in case we have some students or someone joining us right now, let me just give a 30-second recap here. Quantum dot is a semiconductor device that allows you to capture electron and enclose it in all three spatial dimensions. So here in this picture I drawn, the dot would be here, an electron is trapped there, and it can go in and out with this with some rate with this reservoir here. And that is controlled with this gray gates. One great way to measure or check what's happening with your quantum dot is so-called quantum point contact, which is an extra electrode that is sitting here. And then you can measure this current that goes through this electrode that just via Coulomb interaction kind of tells you, is there electron here, is there no electron, what's happening. So you can then take these devices and create multi-qubit or multi-dot chips with them and observe important physics. Quantum dots are super cool because of their scalability. They are so small that in principle you will not run into chip size limitations. What is the downside, let's say, is that these semiconductor devices comes with so much noise and attention and things you have to pay attention to, because after all you have an electron that is sitting in the material, which is, you know, cloud of electrons and other things. So actually address these states properly and build reliable qubits is quite challenging. So when you want to prepare a particular states of this quantum dot, you need to tune the voltages on these gates. And again, we've heard already a number of interesting things about that. I will just give a quick overview on this slide of this tuning procedure. I put some literature selection, but that's just some papers I read and liked lately. It's by no means an exhaustive overview. But one way to think about this tuning process is, I would maybe roughly divide it into these 4 steps, but they of course overlap and may have, and in some cases you will have only 3 and so on. But the first step would be an initial tune-up, just getting your gate voltages into the system that you can sort of have like a few dots at once and a few electron regime. Second would be quantum dot configuration. This is where you decide whether you will have a number of single quantum dots, whether you will have a double quantum dots, triple quantum dots, stuff like that. We heard about from Justina on Tuesday about this kind of tuning. And I actually missed the morning session due to teaching, but I believe that also today you had some nice talk on the same topic by Hendrik and other speakers in the morning. Then when you have the quantum dot and you are in a, say, double dot regime or single dot regime, then there is a more detailed thing, which would be a charge state calibration. So imagine you want to make some qubits. A basis people like to define their qubits is a number of electrons in each dot. For example, you want to prepare a concrete state that has 3 electrons in left dot and 1 electron in right dot or something like that. So that would be a charge state calibration. And final thing, it's a fine tuning, which is what that is exactly, that's super experimental dependent, but that's adjustments of all the final parameters exactly in the regime you want to have them in based on what kind of experiment you are doing. Again, I believe probably Dominic talked about that earlier today. So where we contributed into this big landscape of this full stack quantum dot tuning is charge state calibration, specifically where we wanted to prepare a concrete charge states in double quantum dots completely automatically. So the device we had was a device in the lab of Klaus Enslin and Thomas Ihn at ETH Zurich, and it was 3 quantum dots or a triple dot, depending which regime you are in, that you see here. So there are 3 dots, 1, 2, and 3, and how we wanted to treat this were 2 double dots, dot 1 and dot 2, and dot 2 and dot 3. And in these double quantum dots, we wanted to prepare a concrete charge states. So what happens when you are measuring the device like this? This is again charge stability diagrams that you have seen a number of times during this meeting. So you have a change of your current as a function of your 2 gate voltages. These are 2 plunger gates, but not super important. And every time you have a big change of your current, you cross electron occupancy in your dot. So you may recognize from this that you see this beautiful Coulomb diamond. So we are already in a double quantum dot regime. And when I cross one line, I will add electron in the left dot. When I cross the line again to the right, I would add a second electron in the left dot. And when I go up, when I increased voltage in the other direction, I can add the electron into the right dot. And when I go diagonally, I would add to both, and so on. So for example, if I would now ask you which electron number state is in this place in the charge stability diagram, you would probably take like 10 seconds to calculate it, and it would be very easy to prepare this state. The problem is that to get this kind of beautiful charge stability diagram where you can just with the naked eye calculate your phase transition and just relax and decide which state you want to go to is super data and time intensive. So we wanted to kind of prepare these concrete charge states very quickly while measuring as little as possible. So let me first give you like a rough overview of the whole method, and then in the next slides I am going to explain in a little bit more detail some technical things, how we did it. So first of all, we don't want to start by measuring this whole charge stability diagram. That's kind of core of our issue. So we take only a small patches of it, and we take this patch and feed it into a supervised convolutional neural network. And this network will label the patch based on whether you have transition horizontally, vertically, or both, like you see in these figures here. And based on in which direction you have a transition, the network tells you go diagonally down, or go to the left, or go to the right. So every time we measure a patch, have a neural network decide where are the transition and where should we go next. So we go to the next place, we measure the next patch, and we continue like this until we arrive into the state we want to be in. So we actually trained this model on the experimental data that we labeled manually, and we also augmented them to increase the amount. So specifically, we measured 128 full charge stability diagrams on our device, like the one I showed you on the previous slide. And to that, we added a number of augmentations, like that is something I'm showing you here, where we rotate, squeeze, expand. So we would kind of have a bigger spectrum of these charge transitions that are not just specific to our device, but it would be a little bit more general. Then we wrote a script that cuts out the patches. Now, we labeled these patches in a little bit peculiar way, so I will spend a few seconds explaining this in a little bit more detail. Specifically, we have 3 labels for each patch. So we take this lower left corner and we ask ourselves for each of the 3 remaining corners, what kind of transitions have happened. So for example, if I go from here to here, to the label 1, I see that 1 vertical transition have happened. So between vertical, horizontal, both and nothing, this gets labeled vertical. Then the other corner gets labeled horizontal, and the third corner gets labeled both. The reason we are over-labeling it like this, you see that there is some redundant information in this. Is that because depending on the angle of your transitions in your charge stability diagram and based on how you cut out the patch, it can easily happen that you mistake just visually the vertical transition for the horizontal. So we kind of encoded the information redundantly like this. And then we take these patches and we supervisedly train this network with 3 convolutional layers. And so this like single network that just for a given patch, regardless of where it is in the charge stability diagram, returns these corner labels, has an accuracy about 99%. So then how the algorithm works, it works in 2 steps. First, we find the state 0, 0, and when we have it, we start measuring again and we go from 0, 0 to the exact charge state that we wanted. So I lied to you a little bit on the previous slide for the simplicity reason that for the finding 0, 0, we have slightly different model than for finding MN, but in principle it works the same. But just to say that there are 2 different models that are specifically for finding a 0, 0, we can take a little bit more generous and more coarsely measured patches of the charge stability diagram, because that's way easier to find than finding a very specific charge state. So these are tuning runs on the device. You see that there is some white stuff in the figures because exactly we didn't measure everything. We just measure a patch, we decide where to go next, and we measure next one and next one and next one. So these are the runs that were done to get to the state 2, 1. 2 electrons in the left dot and 1 electron in the right dot. And the green path shows you the path that the auto-tuner took. What I want to point out here is that you see that this is so much more coarse-grained than the beautiful charge stability diagram I showed you on the previous slides, because indeed we just need the network to recognize the transitions, not the naked eye. So even though maybe here or here I would be a little bit unsure, but then I am no expert, the network recognizes it just fine, and then we arrive to the state that we wanted, just like this. Let me say a little bit about the results, because it's not all so rosy as these 2 successful runs that I showed. So we did 160 tuning runs on these 2 double quantum dots. Good news is that we only trained on the first double quantum dot, and when we applied the trained model on the second, it had exactly the same success rate, so this was encouraging. For this finding 0, 0 state, we had about 90% success. For finding arbitrary charge state, we had about 60% success. Here I put a confusion matrix. There is no need to worry about it in detail. It's just to say that like this is the true occupation, this is the predicted occupation, and what you would have is to have all the numbers on the diagonal here. But in fact, what happened is that sometimes we miss a transition, so we have some runs that are off diagonal. Basically, just to address why it's easy to sort of make an error, is that because we have a convolutional network with a finite accuracy. And even if that's 99%, you do 99% times 99% times 99%. And after a while, this drops down quite a bit. But in the end, we were very happy about this because we have this tuning method that is completely PhD student assistance free. And in practice, it means that we need to run it a couple of times to be sure that we are in the correct charge state. Before I move to my next topic, let me quickly connect this to the other super cool talks and amazing sessions at this conference. Basically, anything Q2, the talks I am hearing, they are very much in this ballpark, and especially the session you had earlier today, I think, was particularly relevant. I want to point you to specifically to Justina's talk on Tuesday, where she has this new method to measure only very small parts of these patches I showed you and still have an equivalent accuracy, which was really impressive. Then Natalia Ares group, Dominic, I think, was talking about it earlier today, has this full stack end-to-end from this super rough detuning to the fine-tuning methods that just do everything. And Stephanie Čížek from Roger Melko group did something very similar to what I presented here. It's again about introducing charge states, but she figured out how to make these neural networks as small as possible while actually working reliably. This is super important if you don't want to run it all the time through a computer with a Python that sits next to your fridge, but you would actually want to encode it on the FPGA. It's super important to minimize these architecture. So I just dropped an archive reference here. I am a little bit behind the time, so I will see if I can go through the second part a little bit quicker. So the second thing I wanted to mention is learning the physics of your quantum devices and how that can be helpful to finding this super compressed information such that we don't have to keep training on this super huge measurement data all the time. So I just wanted to give you an example how we are characterizing quantum states of our more difficult devices just from measurement data. So the experimental settings here, it's again an experiment at ETH in Klaus Enslin and Thomas Ihn group, except that the dot now is bilayer graphene. It works just as well as your gallium arsenide or silicon. It's just that you use these 2D material heterostructure, and you may know that unlike a monolayer, if you have a bilayer graphene and you apply electric field, you can open a gap. And opening and manipulating the size of this gap allow you to have this confinement just like any normal quantum dot. You get the Coulomb diamonds, everything. People are looking into these devices because you don't have this spin orbit coupling issues in graphene and things like that. So now there is this generation of a graphene quantum dots. The problem with graphene and other heterostructures is that we don't understand their physics super well. So for example, this is a measurement from Klaus Enslin group. This is in PRX 2018. And here you see each line here is a state. The dots are energies measured in a different perpendicular magnetic field. When you apply magnetic field, you get both Zeeman splitting and also Welle splitting in graphene. So there is basically 4 branches for each state. And then at the time, and this is the picture that is in the paper, these 2 lines, the red and blue, was the best theoretical fit that existed for this experiment. So that's a little bit, let's say, unsatisfactory. So we wanted to redeem this and really characterize these state well, so we could move forward with like defining qubits and having a compressed representation of these states. So, okay, now I don't want to go deep super much into the theory, but there is this super cool PRB paper that writes a minimal model for a bilayer graphene quantum dot that only depends on 4 parameters. First is confining potential that defines the shape of the dot. Second is gapping potential that modifies this gap that you open in a bilayer graphene. Third is a valley number. It's just when you have this valley splitting in graphene, it's a quantum number that tells you whether you are in one valley or in the other. It's just plus and minus 1. And then you have a just angular momentum quantum number for your wave function. Okay, now we forget everything about these formulas. And all we need to know that to make a beautiful wave function that our student plotted here, all I need to know are these 4 numbers, 2 continuous and 2 discrete quantum numbers. So since this problem is so simple, you can basically reduce it to a determinant calculation. So here what I am showing you are plots of such determinants where you have energy as a function of the magnetic field and the color scale is a value of this determinant. So when you have 0, that corresponds to the measurable energy in the experiment. So each of these 0 lines is some state that is just characterized by these 4 numbers. So when we created this determinant density plots, our master student Josef did something amazing that I almost couldn't believe. If you take these density plots and just cluster them, let's not worry exactly about which algorithm it is. It's the stochastic neighbor embedding, but whatever, it's just a fixed clustering algorithm that you can download Python package for. We cluster them and we get these beautiful clusters. So me knowing nothing about graphene, nothing about physics, nothing about this Hamiltonian, I just cluster this data and I get each cluster that is uniquely specified by a combination of these 2 discrete quantum numbers. Okay, in practice, it's not so simple because I will not measure the whole determinant. It's quantum system, so I can only measure the energy that I can measure. And if we only cluster the energies, we will get some mess like this. So that was a little bit disappointing, but we still wanted to fit all of these 4 parameters. And so maybe the reason why I wanted to show this problem is that this is an example where neural networks or other gradient-based methods are not going to work so well. The reason is that the landscape of these 2 continuous potential, the gapping and confining potential, is super poisonous. It's shown here. So you have super long minimum, and I put here for you a white square where there is an actual minimum, but it's like full of this local minima. So any kind of gradient search will just get stuck in random place here and don't find anything. And global methods, they don't use gradient, but just randomly sample the landscape. They are nice, but super computationally expensive to actually do on a large parameter spaces. So what we did was to develop a new method. We used this advantage of writing this Hamiltonian very simply to basically calculate the gradients of this landscape analytically. Like literally, I can just write what the derivative is in terms of the Hamiltonian terms. And then we find exactly where this poisonous valley of the lowest of the many local minima is. And then we use some of these global optimizers that are super computationally expensive on a very restrictive domain. And then what happens is that we can fit the continuous potentials with the precision about 0.2% and find the discrete quantum numbers in 100% of the cases on the simulated data. So that you see the true values here with the crosses and the optimization results with the triangles, and this is just the coloring for which one has which discrete numbers. So I went through this very quickly, but this was just to say that we can use optimization techniques that totally exist, run them on experimental data and find very effective and compact local models. And now this is the results we are getting on the experimental data. So this is the same plot I showed you originally. You have raw data in gray. smoothen data with dashed line, and these color plots are the fits of our fitting algorithm. So we can perfectly find like the local effective Hamiltonian for each state and calculate this energy ladder then. So basically, since we can fit it, then each of these states is fully characterized by these 4 numbers that we fit it only. And because I know the wave function, I can calculate the expectation value of whichever measurement I want. So I will just show you here. This is on 2 more devices, just additional measurements with additional fits, and we are seeing beautiful agreement with the data. So in this second part, I wanted to show you that you can fully characterize a single particle states in the bilayer graphene quantum dot just from a quantum measurement. And again, this is not about building a Hamiltonian that will like allow the next generation discover deepest secrets of graphene, right? It's just like some simple Hamiltonian that capture my physics enough to find some super compressed representation of my states and understand what the ladder of the states is, what they are, how they behave. And then if I know all of this, I can think about how to define a new qubits and things like that. So let me just finish here by repeating this question that I was trying to address in this talk. And I was trying to give you 2 flavors of approaching this that in my opinions are both valid roads to move forward. First one was using machine learning, specifically convolutional neural networks, to do very fast front-end data processing from as little practically needed experimental measurements as possible. And the second, more theoretical line was about trying to make some Hamiltonian learning / fitting / parameter estimation and build effective models for some minimal effective representation of these states, which then has a 2-fold application, which is less data that we need to store and train things with, and deeper understanding of our system for more clever definition of qubits or like experimental design in general. Let me finish by highlighting the people who did the very hard work on this project. So Renato was the master student who worked on the first project, Josef, master student on the second project, and Frank Schaeffer, Benedict, Annika and Rebecca were PhD student and a postdoc who were collecting the experimental data, sharing with us all the experimental details, and helped us optimize all these setups properly. And with that, thank you so much for listening. I also know that organizers set up for me a Slack channel, so I am just putting it here. I'm going to head over there after we are finished discussing that in case someone has any more questions. And with that, thanks for listening.
Thank you very much, Eliška, for such a great talk and also for the very nice overview. Really, thanks. And I do have some questions for you, but let's see if the audience, oh yeah, we already have one question from the audience from Brian Flynn. Thanks for the very nice talk. So he asks, in the UV potential plot, is it never possible that the global minimum is somewhere outside the region you identify?
Oh, this is a great question. Yeah, so we always have to have some bounds for this optimization, and basically what we did was to interrogate the experimental team very hard about because these UV potentials, they are parameters in the model, but they of course correspond to some experimental parameters, at least as far as we understand, one more transparent, in a more transparent way than the other. But basically, we kind of discussed very carefully what is the energy range for each possible potential, and then we try to extend it as much as possible. So this is indeed a great point. I cannot exclude it 100%, but we did maximum to adjust that the boundaries are as reasonable as possible for this.
I see. Thank you. And maybe does Raul? No. Okay. Okay. Thank you. Do we have other questions from the audience? Let's give some time to the audience to warm up. Yeah, we've got another question. So from Natalia. So awesome talk, Natalia Ares. Is there any room for getting a better sense of the Hamiltonian with machine learning?
Okay, let me try to answer, and maybe I will need to ask you for a follow-up question. So there is a lot of situation. You mean extra terms? Yes. Then yes. Okay. Yeah. There is a lot of situations where indeed machine learning is super efficient at this, taking experimental data and mapping it on the Hamiltonian coefficients. And this is indeed something that we did with some of the terms here, just to verify with a neural network that it works. But we ran into this UV problem, so we changed the strategy to the random optimizer. But indeed, it's exactly what you are proposing, because to calculate this Hamiltonian, I have to make some pretty stringent assumption, which you as an experimentalist, Natalia, you would want to strangle me, as in, I assume that the dot is perfectly round, for example, and I say but I should say authors of the original paper. So this is not the case, right? But we can easily make elliptical correction to that Hamiltonian with a perturbation theory. And this is exactly where the machine learning would come in, that you would just use a neural network to find out coefficients for the experimental correction that best fit the experimental data. So this is definitely an exciting research direction here.
Great. Okay, that's great. Do we have other questions from the audience? We still have time for one or two questions. Okay, maybe I can take advantage of this time for one quick question. So I was just curious, maybe can you just quickly gauge how much human input is needed to make all the very nice machinery you presented work, and also to check it, for instance, with the TS and E? I guess it's not that much.
Yeah, so yeah, indeed. Okay, so that depends. Yeah, that depends indeed on the method. Like one thing, so what was somehow the most human heavy for us was this machine learning thing, because we trained on the actual experimental data, and poor Renato had to label them, and that was unpleasant 2 weeks for him. But in the meantime, we learned like some of these things that like Justina Zvolák and Stefany Čížek are doing, that you can do just as well. This theoretical models generate data that look fine enough. So this is a good sign for us. And yeah, with this clustering algorithms, that's super minimal, because there is no even fitting parameters. It's just like a fixed clustering algorithm, and we were so lucky that it just showed all these amazing quantum numbers right away. So there, the only input you need is to kind of understand which cluster is which is really like 1 hour with the Python. So that was pretty great. And then in general, for this big optimization techniques, there is a lot of hyperparameters that one need to fix. But like other than that, it's when it's running, and you don't need any extra human input. Yeah.
That's great. Looks very promising. Thank you. Okay. I think we still have time for one more question, but we already have quite a few, so we maybe have time to add them to Slack. Okay, then if there are no more questions, I would thank again Eliška for this very nice talk. Thanks, Eliška. And yeah, maybe we can move to the next speaker for this session.
Thank you so much for having me.
Thank you, Eliška. Okay, so our next speaker is Ilan Mitnikov. Do we have Ilan?
Yes, I'm here.
Okay, great. Hi.
Hey.
Okay.
Yeah. Oh, I'm upside down.
That's fun.
Okay. Hey.
Okay, hi.
Hi.
Okay, so happy to introduce to you Ilan Mitnikov. He's our next speaker for this session. So Ilan did his undergraduate work at MIT, where he worked with Professor Marin Soljacic on ultra-strong light-matter interactions in graphene. And then after returning to Israel, he joined Quantum Machines, where he's now working on quantum control application development. And today, in his talk, Ilan will present how to boot a quantum computer. So a QA-based graph framework for automatic qubit calibration. So Ilan, take it away. It's all yours.
Yeah. Thank you, Fulvio, for the introduction. Hi, everyone. I'm Ilan. I work at Quantum Machines, or a company that focuses on real-time quantum. Oh, wait, I need to share me. Share screen, 1 second. I'm sorry. Okay, cool.
Maybe let's just take a moment to remember that all our talks will be recorded.
Yeah.
Okay, Ilan,
So,
again.
Yeah. So hi, yes, I work at Quantum Machines. We're a company that focuses on real-time quantum control software and hardware. I'm excited to be speaking to you today about the work we do at QM. We build tools to help our users automate the calibration process of their quantum devices. This talk is well suited between Eliška, who spoke on automated calibration, and Valeria, who will speak about classification. So I'm gonna try to mention both of these topics. Everything I will show you is a combination of offline computation on a regular computer and real-time stages we run on our control hardware, which directly interacts with the qubit on their native timescales of nanoseconds. Before I begin, I want to say some things about who we are. We're a company that focuses on the control of quantum devices. We're about 40 of us, and physicists and engineers who completely focus on quantum control. We are located in Tel Aviv, but also have some employees outside of Israel. Our hardware solution is the OPX. It is programmed using our pulse level language, Qua. Qua. Using both of those, we perform what we call the Quantum Orchestration Platform. The Quantum Orchestration Platform is built to run the most advanced quantum protocols on any qubit platform. We develop dedicated quantum control hardware, which at its heart contains the pulse processor. The pulse processor can take compiled QA code and execute it in real time. This enables the execution of the 4 elements that compose every quantum control protocol. Waveform generation means generating the pulses that implement the quantum operations. Waveform acquisition describes the measurement process, more on this later. And classical processing involves real-time general computation, like Boolean logic and arithmetic. This is very powerful because it allows us to do real-time computations like Bayesian estimation and neural networks and many other things. And we also have full control flow with if, else statements, loops, etc. All this can be done in parallel for multiple qubits. Our QA, our language that we use, looks like that. This is a short program that measures the T1 decay time of a qubit. It's as easy as writing a Python code. I like to go over this thing, but because I'm short on time, I'll just go over the main features. It's compiled on our and run on the OPX. It allows users to change dynamically the pulses in real time on the fly with no need of uploading new waveforms. It allows things like state estimation also in real time, for example, comparing to a threshold. And it supports full feedback operations. For example, if I measure the qubit on the excited state, I can apply a pulse to it. So what does it have to do with building a quantum computer? As we all know, we can't simply run a quantum protocol on your qubits. You need to first do a lot of prep work. There's an old saying in physics, yesterday's sensations, tomorrow's calibration. And it's very clear in quantum computation. In simple terms, you need many experiments before you can run your goal experiment. Even on a calibrated system, you need to be able to track the state of calibration of different parts of the system and to know when things go wrong. To solve this, we have developed Entropy, a graph-enabled experiment runner with automated data collection. Entropy allows you to chain together QA nodes and Python nodes with additional lab instruments on one graph. That can be traversed within a full control flow and looping structures, which make the designing of multi-experiment flow quite easy. The data generated by each node is saved, and each node has a calibration state associated with it to know whether it has been calibrated already or not. I will show you two use cases of Entropy. The first one will be a full automatic calibration of a high fidelity gate. The second one is the use of a neural network implemented in QA that enables multiplexed readout of qubits in real time. So starting with the automated calibration, I feel like I need to say a few things about superconducting qubits and its readout. So the transmon is controlled by charge and flux lines, which control single qubit rotations and resonant frequency tuning. The readout resonator sits here at the bottom. When microwave radiation is passed through it, the phase and amplitude of the reflected signal tells us the state of the qubit. And this state is plotted on the IQ diagram, which can be distinguished between the different states. So how does qubit readout work? We start with an RF signal generated from the LPX. It's ARP converted to a microwave signal. The reflected signal is then down converted in a similar way and fed into the LPX. This mix down and demodulation process performs the following mathematical operation. These weight vectors are then very important to tune when performing the demodulation, and we will discuss how to do that later. Now that we know how to interact with the qubit through the different generated pulses, we get to the first usage of our calibration graph. Our graph will show 5 distinct phases. The first, spectroscopy phase, where we find the resonant frequencies of the readout resonator and the qubit. State discrimination phase, where we learn how to identify the ground and excited states. A second pass second pass calibrating pulse power and frequency, which can send us back to fine-tune again our already found parameters in case things are not working well and are not within our tolerances. And after that point, we're standing on fairly solid ground, so we can start trusting the state estimation to do things like live active feedback. Now I'll go into that in detail. We run this graph on a real qubit, and I would like to show you the results, but this is still a work in progress, and we aren't at liberty to do so at the moment. For now, we'll have to settle on for simulated illustrations of what we actually do. Each of the steps I'm showing here in the boxes are entropy nodes. We first run wide scans of frequency response of both resonator and qubit, and then we fine-tune them, pretty common procedures. The data is automatically fed to a model and passed between different nodes. For modeling, we use heuristics, which we specifically developed for the system we're working on. And it's really easy to modify them to work on any other system and use the same graph structure for any other system. With the drive of the readout resonator tuned, we want to discriminate between the ground and excited states. We want to check if we're excited. I know I am. We measure the IQ plot without driving the system first in the graph on the left. As you can see, it's in its thermal ground state, and we have a small faint shadow. So it's easy to automatically recognize the position of the ground state. Next, we drive strongly the qubit without knowing what it will do, but we drive it strong enough so it gets into a fully mixed state. From that, we can clearly identify both the ground state and the excited state and put a threshold on state assignment. And finally, we choose that threshold and conduct power Rabi. As you can see, the power Rabi is not does not have full fringe visibility, and that is because we start the drive from a thermal state, so we cannot achieve to a pure ground or excited state. Next, with this poorly calibrated pi pulse, we do a Ramsey sequence to fine-tune the qubit drive again. And after having the drive tuned and having the qubit frequency at a good precision, we can do power Rabi again, but this time we use post-selection, and we do post-selection such that we ensure that we start from the ground state. So we measure so we drive, then we measure the data, and we make sure that we start from the ground state. Using that post-selected data, we can find the threshold, the best threshold to be used to have a full pi pulse for the Rabi sequence. And this threshold can also be found automatically. Yeah, so after having a full pi pulse, we can use that threshold and the pi pulse to do active reset, which means reset the qubit better than the thermal state in real time with ultra low latency. So we introduced a highly customizable framework that allows both quantum and classical steps. We start from completely uncalibrated system and achieve high fidelity X gate within minutes. And this time scale of minutes is not dictated by our control system, but rather the quantum device. Using feedback, we can quickly prepare the qubit in a pure ground state. This is still a work in progress, and we hope to release data soon, so watch this space. We acknowledge our collaboration on this part here with Lawrence Livermore National Lab. And now for the second application. So we saw with a single qubit, we have a single drive frequency. Now I'll show you how to scale to many qubits with our framework. To scale up to many qubits, we need to share resources. And a common way to do that is to place all the qubits on a single readout line. So now we have a few frequencies and the signal looks more complex. It looks like that in the frequency domain. And instead of having a pair of demodulations, we will have many demodulations at different frequencies, each with its own weight vectors. And those we can learn. So now for the second, so how do we learn this? We are using a neural network that reads the input and performs the modulations and assigns a state label for the readout state. So you can see that this network, for example, is per 1 qubit. So each qubit has an associated network to it. The output represents the predicted qubit state, which can be either ground or excited, or with lower probability leak into a higher state. This process is repeated. And because we have real-time classical processing capabilities over of QA and our controller, this network from input to output is run real-time on our hardware, and we have a result back within a few hundreds of nanoseconds, so very, very fast. So here we simulated the data for 10 multiplexed qubits, initially with the uniform demodulation weights, as you can see here, and we get poor visibility and distinction between the IQ blobs of the different qubits. And after learning it, the demodulation weights, you can see an optimized view here and a much better visibility for each of the qubit states. So the last simulated example did not consider the interqubit coupling and nonlinear effects of the waveguide, because we had a different network for each qubit. But this can be easily modified to include the nonlinear effect. And here you see we have a nonlinear layer, which takes into as an input all the different results of the demodulations for different qubits. And this nonlinear layer is also run in real time and can be easily implemented and executed with our diverse computational tools. So to summarize, we developed a neural net which optimizes the demodulation weights used for real-time state estimation of multiplexed qubits. It's fully implemented in QA and run on our hardware. This allows real-time ultra-low latency feedback on multi-qubit devices. Thanks. That's it.
Thank you very much, Ilan, for this very exciting talk. It's very great. And yeah, so let's see if we have some questions for you from the audience. Okay, so while the audience comes up with some nice question, maybe I can start with one question for you. So I was particularly interested by so when you mentioned that this is clearly part still work in progress. So I was curious, and I wanted to ask whether there is anything you can disclose with us today, like on what potential directions you might follow, what improvements and upgrades you see in the near future.
Regarding which part exactly?
Oh, for instance, in the first part when you mentioned that this was still work in progress for the optimization, but also in general, if you have anything you want to share.
Sure. So yeah, this work is we're working on a real qubit, and it's very nice to see that even with a little bit of work and heuristics and optimizations developed by us, very quickly we can achieve really high fidelity. And this process is done within minutes. And of course, every team who has their own system and knows it very well, they can develop robust heuristics and optimization techniques which can be implemented in Qua and run on the qubits every time you want to calibrate it, and it's done literally within minutes and no need to wait. And the different neural networks that people mentioned before and will mention can also be implemented on our hardware. It's as easy as writing Python. So, yeah.
Cool. Okay. Thank you very much. And we actually have one question from the audience. So from Brian Flynn, who asks, does this allow you to profile fundamental noise of a device to allow noise inversion on outcomes?
Yes, to some extent. Yeah, we can measure. I have measured noise on real devices, different qubit systems, and yeah.
Okay, and maybe I would like to ask the host to allow Nicholas to answer to that question, if that's possible, if that's still possible. And then also we will have another question right after. Okay, meanwhile, I can go with another question, and then in case we can go back to that one. So from Tundan, can you tell us more about your nonlinear box?
Sure. So the one here. Yeah. So so this nonlinear box is actually could be very diverse. So as I said before, we have a bunch of possible classical computations. For example, here I showed fully connected examples, but we can also do convolution layers related to what Eliška has talked to us before. And yeah, basically we have, you can build your own nonlinear functions with our basic building blocks. We have a lot of them, and these are, and the challenge is to have them run in real time, and that's what we do in real time on orders of hundreds of nanoseconds. Yeah, so.
And we have a follow-up question. Is it a nonlinear filter then?
Yeah, it can be a nonlinear filter, and it can be any other nonlinear function you think of.
Okay, perfect. Okay, thanks.
Thank you.
Do we have other questions? Okay, if not, then I guess we can proceed. So I would first thank again Ilan for this exciting talk. So thanks, Ilan. And then I would proceed with our next speaker for this session, Valeria Cimini. Hi. So it's my great pleasure to introduce our next and last speaker for this session, Dr. Valeria Cimini. So Valeria finished her PhD at Roma Tre University in Italy, and she's now postdoc at Sapienza University of Rome. And Valeria's research interests focus on the development of quantum metrology protocols for photonic sensors. And she has worked on the generation, manipulation, and characterization of photonic quantum states for really many applications. And just to mention a few, also chemical and biological processes. And yeah, of course, she also has substantial expertise on classical machine learning. And that's why today Valeria she's going to talk about the classification of multimode states through artificial neural networks. And I guess this is a pre-recorded talk. So I would then now proceed with this video, and we will have later Valeria here to answer to questions from the audience live. So yes, please, I guess we can start.
Good afternoon, everyone. I'm Valeria Cimini. I'm a postdoc in Fabio Sarrino's group at the University of Rome La Sapienza, and today I will talk about the classification of multimode states through artificial neural networks. I've done this work during my PhD at Roma Tre University in collaboration with the multi-mode quantum optics group of Paris. So the realization of advanced quantum technologies requires the ability of generating and manipulating large entangled states. Continuous variable systems allow to generate high-dimensional cluster states with a scalable procedure and deterministically. Such state can be efficiently generated in optics exploiting multimode squeeze states. However, these are characterized by a Gaussian statistics, therefore they can still be efficiently simulated with classical methods. So the crucial point to reach a universal quantum computational advantage is to include the non-Gaussian features in the set of the available states. But what do I mean when I say non-Gaussian features? So if we have access to the full description of the continuous variable quantum state through on-model tomography, we can reconstruct either the density matrix or its Wigner function that give all the information about the investigated space. The non-Gaussian feature is expressed in the shape of its Wigner function. However, when the number of optical modes or of photons increases, the number of measurements required to reconstruct the complete tomography grows exponentially, making standard tomographic algorithms intractable for high-dimensional systems due to the extremely high computational costs needed to process a huge amount of measurements. However, if we are not interested to recover the complete tomography, but only in the identification of specific features of the state, machine learning gives us some tools to simplify the characterization problem. Here, we are interested to recover the non-Gaussian behavior of the state that is manifested in a non-negative region of its Wigner function. This represents the quantum fingerprint of the expected state. So compared to standard time-consuming tomography protocols, which relies on a maximum likelihood reconstruction procedure, we map the task of the identification of the Wigner negativity into a classification problem that can be efficiently solved with a neural network. Our method consists of training a feed-forward neural network to discriminate between these two classes of states, feeding the network with the corresponding measured data of each state. So, to enter more in the physics of the problem, the class of state that we expected are M-mode squeeze states generated through a parametric down conversion process. We have a nonlinear crystal into a resonant cavity, which is pumped with femtosecond pulses. Such process generates several squeeze time frequency modes that then can be subject to a degaussifying operation. This can be performed heralding it through a single photon detection generated via some frequency interaction between the signal beam and a strong gate beam, in which the charge of the mode determines the mode in which happens the single photon subtraction operation. To train the neural network, we simulate the quadrature's data obtained with an homogene detection scheme, where the signal is mixed with a strong coherent field called local oscillator. They interfere on a 50-50 beam split, and the difference of the two photodiodes current is proportional to the quadrature measurement amplified by the amplitude of the local oscillator. So we simulate the quadrature measurement for different values of the relative phase between the signal and the local oscillator, introducing a random level of squeezing for each mode that is randomly picked between 0 dB and 8 dB. We also perform 2/3 of the time at the Gaussian operation, and we include a random level of noise and optical losses. So to pass the information contained in the quadrature distribution to the input layer of the neural network, it is necessary a binning procedure. The binning is performed independently on each mode of the state for all the phase expected. So in practice, if you consider the 3-mode state, we generate 1,000 of quadrature values for 6 different phases between the local oscillator and the signal. On these 1,000 values, we built an histogram with 5 pins and fixed boundary values between -5 dB and 5 dB. We do this procedure for all the modes of the states, and we feed the network with the occurrence frequencies that we measure in each of these pins of the histograms. So the number of input nodes of the neural network will be equal to the number of modes in the states times the number of the inspected phases times the number of bins of the histograms. For each state in our training set, we also compute the overall minimum of the Wigner function in order to assess the correct label to each state. So we can study the performances that the neural network approach gives in the identification of the negativity of the Wigner function. And to do this, we split the total data that corresponds to 4,000 of total different states into a training set and a validation set. The training set corresponds to the 80% of the total states, while the accuracy is defined as the fraction of correct instances identified in the validation set. So the accuracy, as we can see for the 3-mode case, is really high. We reach the 90–80% of correct identification, while it is of about 85% in the 10-mode states. But it's important to stress here that the standard tomographic technique doesn't allow to reconstruct the complete Wigner function of a 10-mode state due to the high number of optical modes present. So we still obtain a good information that is not achievable with the standard protocols. If we now compare the performances achieved with our method and the ones obtained with the standard protocols, it is of particular interest to study what happens when a limited number of measurements is available. We have done this study for the 3-mode case, that is the only one for which a complete tomography procedure is computationally feasible. So we can see that with the maximum likelihood reconstruction, we obtain a good performance when 1,000 of quadrature measurements per mode are available. However, when we have only a reduced number of measurements, the neural network approach obtain higher performances compared to standard techniques, and they are also with less variability. And this is fundamental if we think about the scalability of our protocol. If we think about the computational time of the two approaches, it's not really comparable, because with the neural network approach, we are studying only one specific feature of the state, while with the maximum likelihood, we are reconstructing the complete Wigner function of the state. So after having trained the neural network with simulated data and studied its performances, we also tested our approach on actual experimental data. Here, the key ability is to know an approximation of the main characteristic of the experimental setup, such as the level of squeezing, of noise, and of optical losses. So we can build a reliable training set, training our neural network, and still obtain a good accuracy in the identification of the interesting feature on the experimental state. We tested this idea with an experimental single photon subtracted two-mode entangled state, and we actually identified with our method the presence of the negativity. Now, to test the consistency and the reliability of the network estimation on experimental data, we introduce a percentage of extra losses in the experimental measurements. This can be done replacing a fraction of the measurement with data sampled from the vacuum state. So we study the neural network response on such state using as a benchmark the maximum likelihood method. So when we introduce an extra level of losses, the negativity of the Wigner function is degraded, and as we can see, we pass from a negative value of the minimum of the Wigner to a positive one when a certain level of losses are introduced in the state. We perform the same study for the same level of losses with the neural network method, but this time we need to test the variability of different training, since the tested state a level of losses that is not included in the state used for the training. So we test the approach on 30 different trainings, and in the bar plot here are reported the percentage of training which gave the identification of the negativity in blue or a positive Wigner function in orange in the fraction of state reported on the x-axis. So we studied for each level of losses 100 different states, and we actually see, for example, for the 2% of losses, that more than the 70% of the trainings identified as negative more than 95 states on these 100 states. The situation is the opposite for the 10% of losses level, where almost all the trainings identified as positive the states in the set. So if we now record only the percentage of trainings that identified as positive or negative more than 95 states over these 100 states, we can compare the two approaches, and we can see that also with the neural network, we see a transition from a negative to a positive minimum of the Wigner when 5% of losses are, extra losses are introduced. We demonstrate also with this study that even if trained with an underestimated level of losses, our approach still gives the correct answer. So the use of neural network in this context offers a technique which is highly accurate and easily scalable with the number of optical modes in the investigated state. We direct probe the interesting feature of the space, avoiding the complete tomographic reconstruction that is computational demanding. The technique results more robust than standard approaches when only limited data are available, and we have tested on high-dimensional states, studying the neural network response on 10-mode states, and the applicability of the approach on actual experimental measurements. The perspectives are now to investigate a wider class of states to verify the applicability of the neural network approach on a more general case. And another interesting point is that it is possible to achieve higher accuracy for the high-dimensional state if we change the binning procedure. Because if we don't fix the boundaries, but we perform an automatic binning, we have already seen that we can achieve the 97% of accuracy even for the 10-mode states. So all the results I've presented today are in this paper, And as I said, it was a collaboration between the new quantum optics group of Rome and the group of laboratory cluster Russell of Paris. Thank you for your attention.
Okay, well, hi Valeria.
Hi Fulvio.
Hi.
Thank you for the nice introduction.
A pleasure, and thanks for this very interesting talk and for sharing with us your great results. So yes, let's see if we have some questions from you from the audience. We still need some time to warm up. Okay, maybe I can start with a quick question. Yeah, so I really looked with interest at your all your results, and I was wondering, since it works so well, can you maybe identify what could be the primary source of error that that can make this approach more challenging, or that can
yeah. So the problem emerges when we go to high-dimensional states. So if we don't have enough measurements for each mode to reconstruct the distribution, we cannot really train the network appropriately. And another thing that we need to manage is that if we have information on the correlation between different modes, in this procedure, we are washing it out because we perform a binning individually on each mode. So for more complex state, we should re-see and the approach to take into account also this information.
I see. But maybe adding some prior human knowledge that is problem specific, this problem can be reduced.
Yeah, otherwise you pass more information to the network, also looking at the correlations, for example.
Okay.
But on this class of states, it wasn't necessary.
Okay, cool, thanks. Let's see if we have more questions from the audience. Okay, not yet. Maybe I can go with another question. I think we still have some time, and also as a we have one question from Natalia Ares. So she asks, what are the next steps? And nice work, by the way.
So the next steps, I think, is to investigate larger states, because like this, we are almost at the boundary of the state that we can look at. And the next step is to look to more specific features and to scale up with the system we are looking at.
Okay. And maybe I can connect to this question and ask another very quick one. Still talking about the next steps, do you think you can extend this approach and maybe apply to some other, like still with metrology, to some other applications, for instance, to I don't know, maybe to classify or study quantum states of light, or some other photonic architectures?
Like for the classification, because another work that I've done is for using a neural network for parameter estimation. There it was a regression problem. Now we are just classifying classes of states. So yes, I think that it can be extended, but it is important to understand if we are looking at specific features of the state, or in metrology, if we want to estimate like continuous variables and pass to a regression kind of network.
That's very, yes, that's important. Okay, thanks. And Okay, I see we don't have more questions from the audience. I think that was really clear. Okay, so I guess we can then thank Valeria again for her very interesting talk, and also I would like to thank all the speakers of this session, and stay with us because now we have our conference picture. So then I would maybe hand it over to the host who can handle this. And then we will have after a coffee break, and then I will see you at 5 p.m. GMT, I guess, here back for the next talk.